Hey guys, so let's pick up where we left off last time with climate systems and climate change. So as a paleoclimatologist, that's what I study, past climate, one of the biggest questions that I get is how do scientists understand that climate has changed in the past, and how do scientists understand climate change that's happening right now? And so there's kind of two ways that scientists use together to make a really good record of what climate was like in the past. So the first thing that we do is we use evidence that indirectly tells us about the past climate record. So we can't go out in the past, you know, except for, 100 years ago, we started using uh, creating really good data records of temperature and precipitation and weather conditions. But before that, we don't really have a lot of instrumental records. And so to stand in for those instrumental records, we have to use some indirect methods to tell us about what the past temperature or precipitation was like. And so that type of data we call proxy data. So we use it as a proxy for some climate condition. And so there's all different types of proxy data, which includes using lots of different isotopes to understand past climate, using the fossil record, and also using changes in lithology, so changes in rock formation methods. And so we also use measurement data, right? So there is some measurements that we can make, particularly um, from ship logs and those types of things. Since humans have been recording things, we can record the gas trapped in ice and actually measure the atmospheric concentration from when that gas got trapped. And there's a whole group of scientists who use computer models to reconstruct climate and to project what climate might do in the future. So thinking about those lithostratigraphic proxies, so remember that in the stratigraphic record, in the rock record, there are sequences of rock that can tell us about depositional environments. So just on a super basic level, right, if you have a coral reef deposit, if you have a limestone deposit, then you know that when those rocks were deposited, that it was a warm tropical marine environment because coral reefs and limestones forming today form in warm tropical marine environments. So that's how we know that our limestones that we have here in North Dakota uh, were formed during a time where North Dakota was closer to the equator and it was warm tropical and marine environment, right? Remember we talked about that earlier in the semester. Another really good piece of evidence would be glacial till, right? So if you have a glacial till deposit, so we also have glacial till deposits here in North Dakota from really recent past, actually. And so if you have a glacial till deposit, that can tell you that it was a cold and continental environment. And so those are two really basic examples, right? There's lots of geologists who look at really small changes in the stratigraphic record, like ratios of grain sizes to figure things out like this as well, and using elemental concentrations of the rocks to figure out how the environment has changed through time. So one proxy that we use to reconstruct past climate is the rock record, right? So what type of rocks are deposited and when they're deposited can tell us a lot about what the past environment and what the past climate was like. So let's think a little more about evidence for glaciation since we just recently talked about glaciers. So if we have glaciers on a landscape, they're going to create the following features in the rock record. So they're going to make glacial till deposits. So remember that glacial till is really poorly sorted sediments with lots of different grain sizes and lots of different shapes of grains. Right, not very well rounded, not very well sorted deposits are associated with glacial till deposits. Because remember, glaciers don't care; they can carry everything. Um, If we have glacial striations, so remember those grooves and striations created by glaciers, if we have those in the rock record, that's indicative of past glaciation. If we have really angular quartz grains, that's associated with glaciation, because if you have rounded quartz grains, that means they've traveled really far, like on the beach, right? But if you have really angular quartz grains, they haven't traveled very far, and that's really associated with glacial erosion. If you have drop stones in a sediment deposit, so remember drop stones are when you have an iceberg, right, and it's carrying some rocks, it's broken off from the glacier, it carries some rocks out into the middle of the ocean, and then it melts and it drops all those rocks out, and they plunk down into the sediment. And also loess deposits. So remember, loess is wind-blown sized particles, silt-sized particles that can be blown in the wind. And so if we have big loess deposits, that's actually evidence for glaciation as well. So here's a picture of some drop stones in Namibia. And this is actually one of my professors that I had at Nebraska, Dave. He's a pretty cool guy. So there's all types of fossil evidence, and you guys are probably familiar with, you know, dinosaurs and the cool fossils, right? Dinosaurs, we have nice, really cool mammoth fossils from later in geologic time, but there's lots of different plants and animals that are sensitive to climate. And yeah, the cool big fossils are fun to look at museums, but the microscopic fossils are typically the more climate sensitive guys. And also they're more likely to be preserved as a whole unit, right? So it's much easier to preserve a really small fossil than it is to preserve an entire dinosaur. And so a lot of paleontological evidence is based on really small fossils. And so using what we understand about modern assemblages, what modern trees live somewhere, what modern algae live somewhere, we can reconstruct what the climate was like in the past. So using changes in the abundance of species or how they're distributed, we can use that to understand what the climate used to be like. And this is a piece of pine pollen. You get brownie points if you can figure out why that is my favorite pollen to look at under the microscope. All right, so here's an example of using pollen to reconstruct past climate. So pollen is a super common proxy to use to understand past environment. It's based on this principle that we understand where trees live today, we understand how their pollen works, and you can use those same relationships tracking back through time to understand what the environment used to be like. So for example, let's say we are looking at pollen found in a pond sediment, and about 12, well, let's just pick something. Let's just pick a place. How about right here in Appalachia? We core a lake. And in that lake record, about 12,000 years ago, we have a bunch of spruce pollen. And today we have no spruce pollen there at all. Right? So here's our site. We have no spruce pollen there at all. So today it makes sense that we don't have any spruce pollen there at all, because all of the spruce trees are up in Canada. And about 12,000 years ago, after we have absolutely dated our lake sediments, we see that we have a bunch of spruce pollen in our record. So we can understand what we understand about the modern spruce forest. And what we know about the modern spruce forest is that it likes colder climates. And it typically lives kind of right up next to really cold environments, permafrost, and that sort of thing. So when we have spruce trees, that means it's colder and drier. When we have more grassy stuff, that indicates that it's a warmer and wetter climate. So from our lake here in Appalachia, we can figure out that about 12,000 years ago, it was colder there than it is today. And this is because we had glaciers in Canada 12,000 years ago that were just starting to retreat. And so the spruce forest was farther down, farther south than it is today. And you can figure that out using little pieces of pollen preserved in lake sediments. Another proxy that's commonly used are isotopes, and there's all different isotopes that scientists use as proxies for a slew of climate variables, but the most famous is the oxygen isotope ratio. It's also probably the most widely used as well. And so oxygen has two main isotopes, oxygen 16 and oxygen 18, and we can use the ratio between those to determine when we have glaciers or glacial cycles and interglacial cycles, or periods of time on Earth where we don't have as much glacial activity or no glaciers at all. So we can figure out when we have glaciers versus when we don't have glaciers from oxygen isotopes, because when water evaporates, it preferentially is going to evaporate the lighter oxygen isotope, the 16. So the 16 isn't as heavy, it's easier to pick up, and so it gets preferentially evaporated. And what happens is that you evaporate water from the ocean, and right, it goes up into the sky, it condenses, and eventually that evaporated water that condenses snows out and starts to form glaciers if it's cold enough. So if it's cold enough, you have snow turning into a glacier, right, through accumulation, and that accumulated water and in that water, those oxygen molecules do not make it back to the ocean, right? So you have 16 preferentially evaporated away. It condenses into precipitation. When it's cold enough, that precipitation stays on the landscape as a glacier and does not run back off into the ocean. And when that happens, you have in the ocean more oxygen 18 in that ratio, because the 16 has been evaporated away and is sort of being held in, it's being held in the glaciers and it's not making its way back to the ocean. So when you have glaciers, you have more oxygen 18 in the ocean, and you have lots of 16 held up in the glaciers. During interglacial periods, the relative ratio of that 18 decreases, and that's because you still have this process where you have preferential evaporation of the 16. So you have your 16 is getting evaporated away much easier. It's still condensing, it's still turning into precipitation and falling at the poles, but if it's warm enough, it's not going to stay as a glacier, right? So it's precipitating, falling, and then it runs back off into the ocean. And so essentially, you have less of a ratio of oxygen 18 because you have more 16 that makes its way back to the ocean. So we can use this ratio, what we understand about evaporation principles, to figure out when we have glaciers and when we don't have glaciers back through time. And that's what this diagram is showing you, the oxygen isotope composition of marine microfossils. And we're going to talk about those in a second on the next slide. And using this isotopic composition, we can figure out when we had warmer versus cooler conditions through the past, related back again to using these two oxygen isotopes. All right, so where do we get oxygen isotopes from, right? So we have to have some record of isotopes in the past. And the main way that this is done in marine records is not just by testing sediment for oxygen isotopes, it's actually by testing microfossils, little teeny tiny fossils in that marine sediment. And particularly, there are organisms in the ocean that make their skeletons out of calcium carbonate. So we've talked about these guys, right? We talked about corals make their shells out of calcium carbonate, but also lots of the plankton, lots of the small organisms in the ocean including foraminifera and nanoplankton, right? These guys are called craccolithophores in this picture. They make their skeletons out of calcium carbonate, and part of calcium carbonate is oxygen. And they just use the oxygen that's in the water and what is available, right? So they record that ratio of 16 to 18 oxygen in their skeletons. And then we can go back through the fossil record and test their skeleton isotope composition to figure out what the temperature was like when they built their skeleton. Because when you have more negative 18 values, that you're going to have warmer temperatures, right? Because when you have more negative values of 18, then that we know that there's more 16 that is making its way back into the ocean. And when we have more positive 18 oxygen values, when the ratio of 18 is higher, then we know that a lot of that 16 is getting locked up in the glaciers, and so we have cooler temperatures on Earth at that time. So not only can we understand these oxygen isotopes using the skeletons, the animals that are living in the water, but we can also test the gas that gets caught up in ice cores to actually take a sample of the atmospheric composition to figure out what the atmospheric composition was like through time. So we have ice cores from Greenland and Antarctica. The longest ice core that we have is from Antarctica, from a place called Vostok there, and your Lab 13 actually has you look at some Vostok ice core data, which is super cool. So we can understand, one, what the chemical composition of the ice is, right? So the amount of oxygen and the ratio of oxygen isotopes within the ice to understand temperature through the past. And also we can use the gas trapped in the air bubbles to understand what the atmospheric composition was like in the past as well. And so in your lab, actually you'll plot up ice age versus gas age, and there is a difference between those two because there's some time from when the snow falls to when the ice gets compacted enough that you can no longer exchange gas with the atmosphere. And so your ice is actually older, and then your gas can exchange within it for a while until it gets so compacted that it can no longer exchange with the atmosphere anymore. So that's why those two numbers are different in your lab. So now that we understand some of the processes used to understand past climate, let's think a bit about long-term climate change and short-term climate change. So long-term climate change, remember, happens on scales of millions to tens of millions of years. So really, really long time scales. And we have two main long-term climate periods or types. So for the majority of time, for the majority of geologic time, we've been in relatively warm conditions with little to no ice, and we call those periods greenhouse periods or greenhouse climates. So greenhouse periods or climates are times when we have little to no ice and temperatures are relatively warm. And then we also have, on the flip side, periods of cold major glaciation events, which we call icehouse climates. So greenhouse and icehouse climates are the two main climates that the Earth switches between through time on millions to tens of millions of years time scales. And these long-term climate changes are related to all types of things interacting, but largely related to how the Milankovitch cycles interact with one another, what the composition of the atmosphere is like. The composition of the atmosphere is largely related to the types of animals that are producing at that time in history. So not only do we have to consider Milankovitch cycles and the animals that are there, we also have to consider how the location of a continent changes through time based on continental drift or plate tectonics, right? So for example, let's say we have our continent, and at time one, it's down here at the pole. So at time one, it is a glacial environment because it's at the poles. And due to plate tectonics, it's drifting upwards. And so through time, right, this same continent is going to have polar deposits, and then it will have a more temperate environment where it might have more stream deposition. Then it will move up into that band of desert climate, right? So where it's having lots of desert deposits, and then it's going to be moving into that tropical realm near the equator where we're getting lots of swamps or reef deposits. And then as it continues to move north, it'll move back through deserts, right, to temperate, to polar. So climate changes based on, again, that differential heating of Earth's surface and where you are located on Earth's surface, which can change for a continent depending on plate tectonic movement. So remember this diagram way back from plate tectonics, where one of those pieces of evidence for plate tectonics is actually that all of the continents in the southern hemisphere have glacial deposits, and if you put them together, you can reconstruct that those continents were all close to, at the South Pole in the past, and you can fit all those deposits together like a puzzle piece to figure out actually what direction the glacier was blowing. So not only do we have to think about where the continents are, what Milankovitch cycles are doing, we also have to think about ocean circulation patterns. So a really good example is when you are opening or closing any ocean gateways, which is going to have a big impact on how heat is redistributed across Earth. So a really, really good example is that in the past, the North American and South American continents had not converged into each other yet. And so, right, the Isthmus of Panama was not there, in that there was movement of currents between the Pacific and the Atlantic Ocean in between the North American and South American continents. Right, so we had one single ocean. But when the isthmus closed, it blocked off this exchange of ocean circulation, right? So that current could no longer flow there. And this started closing about 5 million years ago because of plate tectonics. And because the Isthmus of Panama has closed, it has actually increased the Atlantic Ocean's salinity because there's not this exchange anymore. And is related to the fact that we've had major glaciations about 3 to 2.7 million years ago in the northern hemisphere. So here's a picture of the present day, right, of the Isthmus of Panama closed, and you can see that in the Pacific Ocean we have lower temperatures and salinities, higher nutrients, but there's not that exchange anymore, so we have higher temperatures, higher salinities, fewer nutrients in the Atlantic Ocean as a result of the fact that there's no exchange. And this current that was exchanging is now going up and contributing to the Caribbean current and then the Gulf Stream. So long-term climate change is also related to the composition of the atmosphere, and it's largely related to the amount of greenhouse gases that we have in the atmosphere at that time. So remember that greenhouse gases are the ones that are absorbing and emitting thermal infrared radiation, and so because of that, they are effectively trapping heat within the atmosphere, making it act like a greenhouse. And our main greenhouse gases are carbon dioxide, methane, water vapor, ozone, CFCs. So those are examples of greenhouse gases. And when we have higher amounts of greenhouse gases, we have higher temperatures. And when we have lower amounts, we typically have lower global temperatures. and we can track that relationship through time using our proxies, models, and measurements. So, how carbon dioxide and other greenhouse gases are added and removed from the atmosphere when we're thinking about these really long-term climate changes are really associated with natural processes. So, for example, volcanoes, particularly the gases associated with volcanic eruption, lead to an increase in greenhouse gases, particularly carbon dioxide. So volcanoes, when we have lots of volcanic activity, we have influxes of carbon dioxide into the atmosphere. And this is the main reason why we have a lot of carbon dioxide in our atmosphere when Earth was really young, before it changed to oxygen and nitrogen rich. It's related to lots and lots of volcanic activity when Earth was cooling down from its formation. So we have volcanoes actively adding carbon dioxide into the atmosphere. And then our mountain building or orogenic processes actually lead to carbon dioxide drawdown. And that's related to the fact that you have sort of this flat area and it's getting all crumpled up. So maybe you have some carbon deposits at the surface that would have eroded away, but as you crumple them up, they get preserved, right, and sequestered into that crumpled up mountain process. And then again, if you another process that actually leads to removing carbon dioxide from the atmosphere is burying carbon through burying organic matter. So swamp creation is a really good example of creating a rock deposit out of lots of organic matter, right? And if you're creating a rock deposit, then it's not easily able to be exchanged with the atmosphere like a soil deposit or just something dead on the landscape would be. So let's move away from thinking about these really long-term climate changes, millions to tens of millions of years, to thinking more about short-term climate change. So remember, short-term climate change is things that are happening on tens to 100,000 of years. And as we start thinking about this short-term climate change, we understand a lot about the past 160-ish thousand years at really high resolution. And that's because we have really good ice core records, we have really good rock records as well. And so this diagram here is showing us a record of the last 160,000 years with today over here on the right. And as you go back in time, you can see we have this interglacial period. So when we're talking about the short-term scale, instead of saying ice house and greenhouse, we say interglacial. So a time when there's not main glacial cover. So we have two interglacials during this 160,000 year period. And in between our interglacials, we have a glacial period where we have higher extent of glaciers on Earth's surface. So when we're thinking about shorter term climate change, we're thinking about these glacial interglacial cycles. And these glacial interglacial cycles are related back to our old friend Milankovitch cycles and how those Milankovitch cycles interact with each other. So remember, we have eccentricity, which is our longest scale, longest time period cycle, and it's associated with how eccentric or how round or elliptical the Earth's orbit is. And then we have our tilts, right, our obliquity, whether we have maximum, minimum tilt, or somewhere in between, right, which is sort of the middle period of about 41,000 years. And then we have precession, which is the wobble or whether or not the northern hemisphere faces the sun when we're farthest away from the sun, and that's precession. But when you put all of those things together, it kind of makes this weird combined effect of solar radiation reaching Earth's surface. So it's kind of a complicated signal, but when you put them all together, what you see is when we have less solar radiation, we have a glacial period. When we have these lows in solar radiation associated with Milankovitch cycles, we have the onset of a glacial period. So as we get closer and closer to modern day, we understand more and more about short-term climate change. And that's because we have more and more proxies that we can use because the materials that we're looking at are higher resolution. So they haven't been squished down into a really thin rock layer yet. The things that we can use to understand climate haven't been destroyed beyond recognition, or even those deposits haven't been destroyed. And so we have a lot of deposits, particularly for the last about 20,000 years on Earth, that we can use to understand how climate has changed over the past, 20,000 years. And what we understand largely about the last 20-ish thousand years is about 11,000 years ago, we have something called the Younger Dryas. And the Younger Dryas is this cool period right at the end of the last ice age. So think of the movie Ice Age and that type of environment. The Younger Dryas is this really, really cool period right at the end of the last ice age. And then conditions start to warm. And throughout the Holocene, we have these warm conditions, particularly we have this Holocene maximum, which is what we call it, in between about 8 and 4,000 years ago. And in between 8 and 4,000 years ago, when conditions were warm, that was really good for people because it helped us create agriculture. We didn't have to move out of the way because there was glaciation in our place that we wanted to live, or we didn't have to move because it got too cold. And so this is really when people were able to largely across the world start building cities, right, places that they could stay permanently during the Holocene maximum because temperatures were warm enough for them to make agriculture, right, and produce buildings and that sort of thing. Because conditions were warm, they didn't have to move out of the way when it got too cold in the winter. And then we also have something called the medieval warm period, which was this little warm blip about during the medieval ages. And it's really interesting because you can see in medieval records the fact that it was warmer. People in Europe were doing things that they couldn't do previously because conditions were a little warmer. And then immediately followed by the medieval warm period is the Little Ice Age. And the cool thing about the Little Ice Age is that it got so cold in England that canals started freezing over. And this was recent enough, so not recent enough that we have instrumental records from it, but recent enough, both the medieval warm period and the Little Ice Age, that we have people's diary entries about it, like lots of academics writing about the climate at the time. There's art, right? So not photographs, but paintings of what conditions were like at that time. And so you can really understand this short-term climate change, not only from our climate proxy records, but from some documental records and from some things that humans recorded that maybe they don't even know, didn't even realize at the time that they were recording what climate was like. So for example, there's lots of paintings of people ice skating out, like on the River Thames and stuff, because it was cold enough during the Little Ice Age that things froze over substantially for a long time in England. And generally things don't really freeze over in England because they have the influence of the Gulf Stream, so conditions are a bit warmer, than here in North Dakota. So not only do we have to consider Milankovitch cycles when we're thinking about short-term climate changes, but we also have to think about the fact that the sun actually goes through its own cycles. and it goes through these sunspot cycles where we have a spike or an increase in sunspot activity every about 11 years. And this is related to a magnetic field flip in the sun. So the sun's magnetic field flips and it increases the amount of sunspot activity during that time. And when we have increased sunspot activity, that actually increases the amount of energy that is delivered to the Earth's atmosphere, right? So we have increased influx of solar radiation when we have increased sunspot activity. And when we have increased input of solar radiation, then we have increased temperatures. We also have to consider this variation in the solar cycle. The cool thing about sunspots is we have a pretty good record, particularly from Europe, and I'm thinking there's also a record from China, where scientists as far back as the 1500s were recording sunspot activity sort of as soon as we had rudimentary telescopes. Probably not great to be looking at the sun through a telescope without protective film, but you know, for in the name of science, we have good sunspot activity records from some bored rich people in the past. So if we plot the sunspot activity on a graph, what we see is there's two periods of really decreased sunspot activity. One in the early 1900s, which is called the Dalton minimum, and one at the end of the 1800s, which documents the end of the Little Ice Age. And so you can see during the Little Ice Age, we had this decrease in sunspot activity, and during the Dalton minimum, which is another period of cooler temperatures on Earth. I didn't point it out on the last graph, but it's there. We had decreased sunspot activity. So that is also something to consider when you're thinking about short-term climate change.